All right, so hello everyone. I'm very excited to announce Professor Anna Lauscher from the University of Hamburg, who was at the same time as me approximately doing her PhD at the University of Mannheim, so we know each other for quite some time. Today she's going to talk to us from peer review to particle accelerators, generative AI in science, which is a really topic that is very dear to my heart, but also to many of you here. And just a few words about Anne. She's a professor of Trustworthy Artificial Intelligence at the University of Hamburg, where she leads the Trustworthy AI Lab. Her research connects state-of-the-art generative AI with questions of fairness, inclusion, safety, robustness, and the societal impact of large language models and their multimodal extensions. Before her current role, she was Associate Professor of Data Science at the University of Hamburg Business School and a postdoctoral researcher in the Natural Language Processing Group at Bocconi University in Milan. There, she worked on incorporating demographic factors into language technologies to improve both performance and fairness. And prior to that, she received her PhD with highest honors, so summa cum laude, from the University of Mannheim, focusing on the interplay between language representations and computational argumentation. During her academic career, she also held research roles with Grammarly and the Allen Institute for Artificial Intelligence. Her work has been recognized with multiple awards, including being named one of the 100 billion women in AI ethics for 2023, and one of the leading 30 German AI experts and academics, an award that she received in 2025. So without further ado, Anne, thanks a lot for your time to talk to us today, and the floor is yours.
Yeah, thank you so much, Kirill. I'm now sharing my screen. Can you see it?
Yes, we can see it.
Okay, perfect. Thank you so much for the kind introduction and also for the invitation. Of course, I'm really happy to be here today. And yeah, without further ado, let me start. Maybe let's look back for a second. So it's already been 3 years now since generative AI has reached the general public. And I guess you still remember all the news. ChatGPT, the OpenAI system, which sparked the hype at that point in time, was really called Google Killer and quickly reached 100 million users only 2 months after its launch. So it was really the fastest growing web platform ever. And also the ways the system has been used made it to the news. And I think now, 3 years later, we can for sure say that these systems have already changed our daily lives for many of us, specifically also researchers in this room, and they will continue to increasingly be part of our lives. And similarly, for us as researchers and scientists, we can already say that they will change the way we do science. But what does that mean? What is science even? Science is both a complex system and a complex process. We search literature, we generate ideas, we run experiments, we analyze data, we iterate, and we review papers, communications from other authors, we communicate findings, and depending on the particular discipline, we operate also increasingly complex scientific infrastructure. And so you can see it involves many, many authors, actors, it involves many, many steps. And traditionally, humans have performed all of these tasks directly. And in this talk, I'm going to argue that AI systems will increasingly participate throughout this process. And they will participate not only as passive tools, but increasingly also as collaborative agents. Agents that can also search and find literature and analyze and generate hypotheses and interact with the infrastructure and so on and so on. And thus, hopefully help us scientists and researchers to navigate increasingly complex environments. What I'm going to do in this talk is that I'm going to present depending on the time, but I'm aiming for 4 illustrative examples from our own research. The maybe most traditional one, and maybe also the comparatively most simple example, is scientific content generation. So here it's about supporting authors in writing a nice manuscript. And I think the writing support is something that probably all of us in this room are already using. But one aspect which I don't use very much yet is scientific figure generation. Why? Because even though modern text-to-image systems are increasingly impressive, they often struggle with scientific figures. For instance, also because the prompts may be really, really complex. Like, for instance, there is an example on the left side of the slide where you can see also on the top a generation of GPT-4, and the prompt is given in the caption. The prompt is average relative loss in bioencoder recall accuracy on NQ by recall set size depth on the baseline pre-training alignment, data augmentation and contrastive alignment post-training on noisy queries. So even for a human, it's not so easy to understand what should be done. And moreover, in science, we require precision, right? So we really want nice figures, high quality figures that have a lot of structure. And as we can see here, it's really difficult for the system. So in the example, the system was able to generate a 2D plot with access and also labels, and the title is there, but there's no other content. Moreover, the standard raster graphics, which are produced by most text-to-image models, they are not desirable in science because they often fail compliance with the journal requirements. We require vector graphics, which also don't have any resolution issues in comparison to these raster graphics. And moreover, they are not easily editable, so I cannot really modify them precisely in a very easy way. So we want vector graphics, and in a work that I show here, our idea was to leverage TIX for this. TIX is integrated in LaTeX and allows us to basically code vector graphics. And these vector graphics then fulfill conference and journal standards and come with high resolutions. And moreover, because it's TIX code, I can really edit every single line and really control how my figure looks like as an author. And this is what we target in a work which was presented in 2024. What we did was we first collected a large-scale data set with captions and TIX code, mostly from a variety of sources, for instance, from arXiv or from TextExchange. And it consists of 120K TIX drawings and captions. Then we also fine-tuned an existing model, Llama, on the data. And our TIX-tuned Llama performs in our evaluations, and in particular in the human evaluation, better than GPT-4 or Claude, which were the systems which we tested as state-of-the-art comparisons at that point in time. And then we also presented a variant of Llama, which was augmented with multimodal clip embeddings, which we call Klima. And Klima is shown here together with illustrative examples. So on the left side, you can see example captions with which we can prompt the model, and on the right side, real outputs of the model. For instance, a 3D contour plot with a caption on the top left and the resulting figure after the TIX code has been compiled on the right. And the idea of Klima is that on the one hand, the caption is fed directly into the fine-tuned Llama. And on the other hand, we feed the caption into Clip and obtain an embedding, which we can then use as a soft prompt to augment the prompt input into the model. Yeah, let me move to some results. One thing that I want to say is that here you can see Klima in a 13 billion variant, and in a second variant where we additionally feed images into Clip and obtain image embeddings. We evaluated of course, our approach also automatically and not only with humans. And here you can see that we report multiple measures. For instance, we use CLIP score, which is really an established score to compute the similarity between a text and an image based on the CLIP embeddings that you produce when you feed text and image, which tells us how close the produced image is then to the input prompt, basically. We can also compute an image-image similarity based on the CLIP embeddings. There is, for instance, this kernel inception distance score, which assesses the quality of generated drawings by comparing their distribution with the distribution of real images in our test data set. Crystal blur is a code similarity measure. There's the extended edit distance, which is a string similarity that we apply on the code. And in addition, we also compute compilation sampling rate. So basically, how often do you need to sample so that you get code which actually compiles? And some of the scores would be better when it's higher. And for instance, for the sampling rate, lower would be better. But we have inverted this here to show it nicely on the graph for the CLIMA model, GPT-4 and Claude. And what we can see here is that GPT-4, which was the strongest reference system scored really high on this compilation sampling rate. So it really produces code which is valid. And then also it performed very well on the CLIP score. And because it did not perform so well on the other dimensions, that made us a bit suspicious. And so we double-checked the images manually that were produced, and we found that, as also shown in the example that I showed you, this effect relates to the fact that the model tends to put parts of the input prompt into the picture, into the figure that is produced as a title of the figure. Like for instance here, and then you get high similarity scores with the text. And we did also an additional experiment where we cut those out, and then the score immediately drops. Yeah, our CLIMA models performed well on most of the dimensions. So even though they are much smaller, they are competitive with the, at that point in time, state-of-the-art models. And then, as said before, we also conducted a human evaluation where we showed a reference caption to 4 annotators and 4 images. And each annotator had to select the best and the worst image. And based on this, we can perform a so-called best-worst scaling, which gives us score ranging from -1, which is not great, to 1, excellent. And the results in terms of density are shown here. In red, we also show how the human-created reference images performed. And of course, they score the highest, which validates basically also our evaluation. And as it can be seen, CLIMA in the 13 billion variant, as well as the Llama version, which we fine-tuned in the 13 billion variant, score relatively well, mostly similarly. And in contrast, GPT-4 does not seem to produce great images that really match the caption. Yeah, what is it what we learn? I think my takeaway here from that case study is that in the domain of science, because it's so complex, often domain specificity really, really matters. So it makes sense to fine-tune models. And in this case, then also the smaller models can outperform models that simply rely on upscaling data and upscaling parameters. Let us now move from scientific content generation to something that I find personally very, very important, scientific evaluation. Peer review. Peer review is really the highest quality standard in science that we have. It's a super sensitive process. And of course, the question is, how can we optimally support reviewers and other people participating in peer review in their roles while maintaining scientific integrity? And this in light of the increasing number of scientific publications which are submitted to the venues. In one work, we explored the concept of lazy thinking for this purpose. What is lazy thinking? Lazy thinking is, in the context of natural language processing research paper reviews, the practice of dismissing or criticizing research papers based on superficial heuristics or preconceived notions, rather than thorough analysis. It is characterized by reviewers raising concerns that lack substantial supporting evidence. So it's essentially a quality issue with the reviews. And this definition is taken from the ARR 22 guidelines. So this is from the ACA rolling review. And moreover, in these guidelines, there were specific types of lazy thinking issues listed. I show you a screenshot that I took last summer. And maybe you have seen this list also before, as many of you are probably reviewing. So for instance, one of these lazy thinking heuristics would be the results are not surprising. And then they say, why is this problematic if you say this as reviewer? You're not surprised by the results and therefore the paper is bad. Well, because many findings might seem obvious in retrospect, but this does not mean that the community is already aware of them, and therefore the science may anyways be valid. Or H2 was here, the results contradict what I would expect. And yeah, this may be a sign that something is off, but on the other hand, you may also just be a victim of confirmation bias. So without further justification, this is not a valid criticism. And in order to tackle these lazy thinking issues in natural language processing peer reviews, we created a novel data set where we really annotated these issues in peer reviews. Our data set comprises 500 expert annotated review segments tagged with the 18 classes that we got from the ARR guidelines. So for instance, the most common issue that we found was that people kept asking for an extra experiment without it being necessary for the validity of the overall conclusion. Yeah, and then you can, of course, try to detect these issues automatically to support reviewers and to give them feedback on their reviews to raise then in turn the quality of the reviews. And this is what we did, and we experimented with multiple approaches. There's a set of experiments in our paper. For instance, here I show results on the one hand, the coarse-grained classification. So is there a lazy thinking issue or not? And the fine-grained classification. So which of the 18 classes is present? And what we do here is we test several models, for instance, Gemma, Llama, Mistral, Quen, so on, in a zero-shot setup and a one-shot setup. And later in the paper, we also conduct fine-tuning, instruction tuning with the models. Yeah, first, maybe some baselines. So you see that the fine-grained classification is really difficult with accuracies hovering around 5. And this is because we have 18 classes. It's just very difficult. And when we now move to the models, the first thing that we can observe is that having an exemplar, a demonstration in the prompt really helps a lot for some models. It helps all across the board, but the largest gain we obtain is 31.7 percentage points. This is always what is shown in the parentheses compared to the zero-shot performance, which is given before. And then our best model reaches 56.4 percent accuracy, and this is Quen. And then later in the paper, we show that the fine-tuning further improves these results. But I think this is not so interesting. Can models do this? Yes or no? How good are they? And so on. I think the real question is, of course, does it really help? And who should it help? Well, it should help reviewers to improve their reviews. So as complementary to the NLP experiments that we show in the paper, we really conduct a very, very small controlled experiment as the final part of this work, where we sample 50 reviews existing from the original corpus, and we do a rewriting study. We compose two groups of 2 PhD students each. And in group 1, the PhD students have access to the review and the ARR guidelines, and they are asked to improve the review. And in the second group, they have the review, the guidelines, and in addition, annotations coming from our model. And they are also asked to improve the review. And after the reviews are improved, we conduct an additional manual evaluation with 1 PhD student and 1 postdoc, and we rate the reviews for their constructiveness, justification, and adherence. And the result was encouraging. So reviews improved substantially in terms of constructiveness, justification, and adherence to reviewing standards. So it means that actually AI can help us to give better feedback to each other and therefore can raise the quality bar. So here AI is not replacing reviewers. Instead, we want it to act as an assistant that supports higher quality scientific discourse. And my personal takeaway is that specifically for these very sensitive aspects of the scientific process, this is much better personally for me, much more preferable and meaningful than full-blown end-to-end automation. But let us move to a setting which is maybe a bit more ambitious even, AI systems participating directly in scientific discovery. So this work, which I show here, was evaluated on the so-called LHC Olympics Anomaly Detection Challenge. This is a community benchmark competition in high energy physics focused on discovering new physics. So signals in the data, and the data comes from the Large Hadron Collider. And you should use machine learning-based anomaly detection, basically. So the idea is that participants are given large data sets of simulated particle collision events. And most events in this data come from some standard physics models, but hidden inside some of the data sets, there are unknown signals, anomalies that could potentially represent new particles or new processes, so new physics. And the goal is to detect these. Yeah, and that is complex. That is a complex challenge. And we tested whether we can design a multi-agent system that can perform the task decently. The agents, so it's a multi-agent system. That means there are multiple LLM-based agents inside that have access to tools. They can perform their own analysis, and they can explore the data. And in our design, we defined particular roles. So let me guide you roughly through the process. We start with the task, and the task is put to a stack of tasks, which is managed by a task manager. And this is some kind of other system. And the task also goes to our first agent and the main agent in this system, which is the so-called researcher. And the task is basically a prompt. And the prompt is something like, I will only read it to you roughly because it's very complex and long. You are giving a data set consisting of events. For each of these events, the data set contains the following features. The data set is stored as pandas data frame. And there might be new physics well hidden in this data set no one else has found yet. Being the best physics AI, you are the last hope to find new physics, and so on and so on. So basically, you describe really what this challenge is about. And now the researcher can do multiple things. For instance, split this big task up into multiple smaller tasks and add them to the task manager, and also mark when a particular task is completed, for instance. Or it can interact with the local machine by writing files and specifically writing the final report in which the results should be stored, or also reading files or executing some code. And it can hand off some tasks to a coder agent, which can write Python code. And this is an iterative process. So when the coder writes Python, then we send it to a linter. If the linter says, oh, well, there are errors, then we regenerate the code. But if there are none, then we have an additional agent, which is the so-called code reviewer, and can give feedback to the coder so that the coder can also iteratively improve the code. And last, we have one agent, which is the so-called logic reviewer, an agent that specifically should give feedback to the researcher in terms of the overall research logic. And it can, for instance, check the final report. Yeah, and then the researcher can run this process and at some point end the project, and then we are done. And I'm not going to show you detailed results because we computed many, many measures for many models, and because these are all, yeah, very domain-specific numbers in terms of the domain performance, physics performance. But overall, we found that really the most advanced models, and in our case, specifically GPT-4, achieved performance comparable to human-developed approaches. So the model was even able to choose approaches that were similar to what humans would do. Yes, so something that, like methods that resembled the state-of-the-art anomaly detection techniques used by physicists today. So I think all of this suggests that modern AI systems, they are really beginning to approximate the forms of scientific reasoning or methodological selection, maybe better, that humans do. So this is something that I think is currently very, very hot. And there are also results from other works that show that these modern AI systems are really, really good already in these kinds of data analysis scenarios where you really need to experiment also, maybe also idea generation, which we did not target in this work. And I think here specifically these multi-agent systems may provide a viable solution. But also, of course, there may be problems occurring when you let multiple agents interact. And this is something that we want to investigate more in the future. But last example, there is something which I feel is sometimes a little bit overlooked in the literature on AI for science, specifically in the NLP community, which is that AI is not only entering scientific analysis and peer reviewing and so on, but also entering everything around the scientific infrastructure itself. In this context, I have collaborated in the past 2 years, and I still collaborate with scientists from DESI. DESI is short for Deutsches Elektronensynchrotron or German Elektronensynchrotron. And this is one of the leading research centers for particle accelerators and fundamental physics research, which is also part of the Helmholtz Association, Germany's largest scientific research association. And on the slide, you can see how it looks like in Hamburg, actually, in the so-called Science City in Bahrenfeld. So on the slide, you can see the DESI campus, and some of its major facilities are highlighted, in particular the Petra 3 Flash and the European XFEL, which are large and complex accelerator-based systems. And they operate really continuously 24/7 sometimes. And you might imagine already that there's a lot of complexity involved. And in the first work that I want to show you, or one project that I quickly want to mention, we explored human AI collaborative particle accelerator tuning using large language models. And the core idea here is that the tuning of these particle accelerators is very complex. I don't understand it because I'm not trained for this, of course. But you really require domain-specific knowledge, and it's a bit tedious and so on. And therefore, people are looking for methods that can support the operators, the human operators, to tune these systems more or less automatically. And what we did here is that we demonstrated that LLMs can be used to tune these particle accelerators, and how. So on the top of the slide, a particle accelerator is shown schematically, and the green thing is the beam, the particle beam, and this is what you want to configure basically, or control. And you can control it via a set of magnets, for instance, that all they're of different types and they have different parameters. And the tuning process involves setting all these parameters such that the beam looks exactly like you want it to look like for a particular experiment. And how do we use LLMs now in this process? Where we prompt them with a task description where also the magnets are described, for instance. And then we also say, and also the goal is described, like how the beam should exactly look like. And then we also tell the model that it needs to produce parsable output, in our case, JSON. We prompt the model, we obtain a response, we pass the JSON, and in the JSON now there are the parameter set for these magnets. And then we can configure basically the machine with these parameters that we get. And we obtain a particular beam. The beam is observable with something like camera, so we know how or what the effect of this particular configuration was, which we can then use in the next iteration as previous input-output examples to guide the model towards optimizing the tuning. Yeah, so we demonstrated here that LLMs can be used to solve this complex task, which is also, or was one of the first examples of general numerical optimization with large language models in an iterative manner. But compared to the state-of-the-art particle accelerator tuning algorithms which exist, for instance, based on reinforcement learning approaches and so on, we found that LLMs are not yet competitive at that point in time. And we also have another project currently running where we focus on AI-supported exfil laser operations. This is also funded by data science in Hamburg, Helmholtz Graduate School for the Structure of Matter. Dash. And what is the idea here? Well, I mentioned already that these facilities, they are running often 24/7, and the organization needs to ensure uptime because researchers actually want to use these facilities and they apply for beam time and so on. And therefore, they have many human operators which always monitor what the systems are doing and fix issues and so on. And in this continuous operation, they document observations, for instance, they document failures, they take actions, they document what kind of actions they take, and there is a ticketing system and so on. So there is really a large collection of real-world operational data for lasers available, which we use as a foundation for this project. And at the moment, we have just, LREC was 2 weeks ago. Also, there we have presented the first publication resulting from this project where we create a proper data set from all of this operational data for issue detection and category classification in these laser logbooks. Yeah, so with these two examples, I wanted to show that I believe that there are even more interesting problems in the complex systems of science that you can see, then natural language processing is largely targeting at the moment. And while what we have seen so far are just a few examples, I think what we can already conclude when looking at this diagram, and what you may have experienced also already yourself when coding, vibe coding, and when writing and so on, that we are welcoming also a new world of science in which AI agents are involved. AI can significantly support and accelerate science, but of course, and this is very important to me to say, and what I always want to emphasize in all the works that we do in this direction, specifically also when it comes to sensitive aspects such as peer reviewing, is that it also introduces risks, which we must not forget. For instance, the issue of bias. Unfair and exclusive biases, for instance, in literature recommendation, in summarization, in review generation, in citation generation, unfair treatment of minoritized groups based on their institution, gender, some other proxy inference based on the name, and so on. Then also transparency issues. So for some systems, it might be largely unclear how they are operating, and therefore we work also in this direction, of course. Hallucinations. I think very important topic, specifically when it comes to science also. And here is one example that I just want to show to illustrate this issue. And here, actually, I show you a reference or, bibliographic entry from a list of references from the paper in the back, where the first work that I mentioned today is cited. And as you can see that in the first version of the paper from January, 2 of 3 author names were distorted, including mine, which of course, when my collaborator told me about this, I was a little shocked, but also I did not take it too personally because mistakes happen. I also make mistakes and so on. But the problem is that when these papers are written with AI support, and AI support produces these mistakes in references or even produces fabricated references and so on, that means that it's not only personal, maybe, but this is happening at scale. So these issues are threatening also the integrity of science, a system that is important for our society. So it really has a societal dimension. And I quote here from a statement, which I will show you in a second. A citation is a formal assertion of a relationship between works, and when that relationship is fabricated, the integrity of the entire document and the scholarly record is compromised. Contamination of the scientific literature has further serious consequences in propagating ghost references, with a knock-on effect on general information proliferation and the establishment of non-existing knowledge sources. Yeah, this quote comes from the recently released ACA statement on desk rejecting papers with hallucinated references, which where they identified over 100 papers that contained citations to non-existing literature, where of course it may be an issue relating to AI-generated hallucinations. So it's a real issue that personally affects us, but that also affects society at large, and where publishers and communities also need to act upon. Yeah, and there are other issues, like for instance, a potential streamlining of research, by which I mean that potentially underrepresented research paths, maybe topics which are not so popular, ideas which are a bit niche also, might be further marginalized. Then the speed of AI-based science. When everything can be done automatically, how do we ensure ethical oversight? And then there are also the other safety aspects, which are typically mentioned, like, for instance, the issue of adversarial use. So I believe that one thing that we are as researchers and scientists supposed to be really good at becomes even more important than ever before. And this is critical thinking. And with that thought, I'd like to end my talk, and I thank you very much again for listening and for the invitation.